Okay. So, last class we have discussed about the perception of amplitude, or you can say the perception of intensity, that is loudness, and how the loudness is converted into dB, what is 0 dB, what is equate loudness curve, what is Sloan curve, that we have discussed. Today we want to discuss about how human being perceive the frequency. If you see that we have the pitch, we generally call the pitch of this sound is very high, pitch of this sound is very low, your pitch is very high pitch. So, what is pitch? So, pitch is a perceptual parameters, whereas the frequency which is related to the pitch is the physical parameters. Frequency can be measurable, but pitch is a physiological parameter which is perceptually measurable. So, this is a perceptual parameter. So, pitch and frequency are not same. If I say pitch is a perceptual of the perception of the particular frequency. If the frequency is not in a pure tone, then the pitch may be different from the frequency. Like that, if I give an example, you have heard it, that suppose there is a harmonium and there is a guitar, there is a let us say sitar, there is a string, different kind of string instruments are there. Every instruments are playing the let us the bass sa, which is a particular frequency, let us 250 hertz frequency. But if you perceive the sound, you can easily understand which sound is coming from guitar, which sound coming from sitar, which sound is coming from other string instrument. So, that means the perception of frequency is not as that the physical frequency. So, pitch is mainly a perceptual dimension of the frequency, and the pitch mainly corresponding to the fundamental frequency, but not it is one to one corresponds. Okay. We have to interest that human being, suppose human being perceive the frequency, yes, we perceive the frequency. How good we perceive the frequency? That means in which scale, in which how you perceive the frequency. So, suppose I have a x axis, there is a scale physical frequency in hertz. Okay. Now, I want to know if I perceive the frequency, what is my resolution power, in which scale a human being, normal hearing human being perceive the frequency. So, that scale is called male scale. What is, there is a logarithmic scale, male scale. How it is derived? Now, suppose I do a perception test that I varying the frequency of a pure tone signal and playing that signal in a normal audio or microphone in a loudspeaker, and I told the listeners, when you perceive that the frequency is double, then raise your hand, like that amplitude. So, I can develop a scale on which human being perceive the frequency. If you see, it will come look like this. So, this scale is called male scale, which is a logarithmic scale. Okay. So, I can say the human perception of frequency that I can derive by experiment. This axis the frequency. So, I generate a pure tone of different frequency, and I generate a pure tone. So, suppose I generate a pure tone of 50 hertz, then I said that you raise your hand when you perceive the frequency is double. So, let us it is come around 100 hertz, then I just 55 hertz, all kind of variation I play, and he raise in here, raise a hand in here, raise hand in here, like here, then maybe here, then maybe here. So, from that point I can draw a curve and find out that the perception of the human, your frequency perception of a human is not linear. Initial period maybe up to 500 hertz, to some 500 hertz, its scale is linear, but after that it becomes a nonlinear scale. Okay. This scale is called male scale. So, in male scale I can derive the mathematical equation of this curve, and in male scale, in pitch in male, there is two equation, I can use any one of them, like 3322 log 10, 1 plus f by 1000 or 1127 log E 1 plus f by 700. So, this equation is actually fitting this curve. So, this equation is called pitch male scale male equation, okay, pitch in male scale. So, suppose I have f is equal to 2 kilohertz, then I can find out what is the value of the f in male scale. So, I can put that pitch in male scale, let us pitch in male scale male is equal to 1127 log let us E 1 plus 2 kilohertz 2000 divided by 700. So, I can find out the male frequency. Okay. So, this is called male scale, you can say male scale conversion of the hertz to perception of the frequency. Next, you heard that I have discussed it during that base layer membrane, that we perceive that each sensor along the base layer membrane is corresponding to a particular band of frequency. So, that means the ear cannot distinguish the sound within the same band that occur simultaneously. Suppose a cochlear that along the base layer membrane particular band of frequency is perceived by a one sensor. So, if within this band if the frequency occur, then I cannot distinguish the difference between the two frequencies. So, this band is called critical band, critical band. So, the auditory system can be roughly modeled as a filter band consist of 25 overlapping band pass filter, which is varies from 0 to 20 kilohertz. So, that band, so I can say, okay, instead of human auditory systems, I can think about the engineering model of some band pass filter whose frequency bands are nonlinear and 25 overlapping nonlinear band pass nonlinear bandwidth band pass filter can be completely model the human auditory system. Then bandwidth of each critical band is about 100 hertz. Okay. So, signal below 500 hertz it is linear, and if it is increased above 500 hertz it becomes non-linear. So, that bandwidth is defined as a bark. So, one bark is equal to width of a critical band. So, bandwidth in bark scale. So, bark scale is equal to f by 1000 if f 500 hertz 9 plus 4 log 2 f by 1000 sorry 100 1000 if it is f is greater than 500 hertz. So, that means within 500 hertz bandwidths are 100 hertz bandwidth with overlapping if it is 50% overlap. So, that is a band 100 hertz bandwidth, then from 50 hertz another 100 hertz bandwidth. So, up to 500 hertz bandwidth are linear 100 hertz. After 500 hertz the bandwidth is non-linear. Okay. So, I can find out how many critical band is required to cover the 0 to 20 kilohertz. Okay. So, that bandwidth is called bark scale. Okay. So, this is the critical band pictures of critical band, and I will discuss with when we do think about the MFCC kind of things. Okay. This is a bark scale. Next, another phenomena is called frequency masking. So, perception of frequency and another is called masking. So, what I said, the human being has a threshold of hearing. So, threshold of hearing curve, I can say this is the frequency and this is the threshold of hearing. Okay. Now, it is said that presence of a particular tone, if some tone is present in here, pure tone, suppose some tone is high tone is present in here, then it is said that nearby bandwidth, the threshold of bandwidth, threshold of hearing bandwidth will change. That means, if there is a strong particular tone is present, less f is equal to 1 kilohertz, 1 kilohertz, let us 1 kilohertz, then nearby frequency threshold of hearing is shifted upwards. So, I cannot perceive, if it is this tone is not present, I can perceive this frequency, but since this tone is present and if I have a frequency amplitude of like this, I cannot perceive it. It required a amplitude to cross this limit. Okay. So, that means I can hide this frequency because of presence of this strong tone. So, this phenomena is called frequency masking, and this is utilized in speech coding to hide the noise. So, suppose the coding generate a noise, if the noise is within this limit, then I can say this noise is not perceivable. So, to hide this noise, frequency masking is much more useful. Okay? I am not going details about the frequency masking, there is a lot of details on frequency masking. So, if you are studying the speech coding, then auditory masking is very important. Next one is different view of auditory perception. So, there is I can say the auditory perception has a two view, one is called functional view, which means suppose I cannot know what is happening in here, I cannot do the anatomy and I cannot biological system I cannot measure, but if I consider the human head or human auditory system, perception is nothing but a black box, which I discussed in the first class, then I can say I can stimuli the systems. So, I can excite the system by a known stimulus and then I can measure the physiological behavior coming out from the system. Like that the development of Schoen scale or male scale is the example of functional modeling. Another one is called structural modeling, based on the study of physiology or anatomy, how various body parts work with emphasis of or emphasize on the process neural processing of sound. So, this is another kind of study, the structural study. I have to analyze a human anatomy, excited the signal, measure the nervous signal, all kind of things can be done, which is called structural analysis. So, I can say the functional analysis, like that how human being perceive the frequency is the functional modeling. I play a different sound and a human being listen the sound. So, I excited the human perception by external stimulus, which is known stimulus, and observe the output, then can try to develop the how human being perceive the frequency, that scale, that is male scale. So, that is functional kind of auditory perception. Okay. Second one is that why we have to know the perceptual modeling or how human being perceive the frequency. So, perceptual effect include the most auditory model, spectral analysis on a nonlinear frequency scale, spectral amplitude compression, loudness compression via logarithmic scale. So, we are not you can say that physical loudness is not physical intensity is not equivalent to the perceptual loudness. So, there is a logarithmic compression is there. Decreased sensitivity at lower frequency, you know that lower frequency we are sensitive to the lower frequency, but higher frequency average, there is the bandwidth, the critical band is very big. So, average, so resolution, human resolution of the higher frequency is very rough, I can say roughly approximate. So, I can say decreased sensitivity at lower frequency and increased sensitivity at decreased sensitivity at lower frequency, or you can say the change of perception of the frequency and lower bandwidth is much linear and the upper bandwidth is non-linear. Then utilization of temporal features and auditory masking of tones. So, those phenomena can be used in auditory modeling, or when we extract the speech parameter from the speech, we have to include this perceptual variation, so that the parameter directly represent the human speech perception, what we have done in the inside the ear. Okay. So, that is called perceptual modeling. So, the different auditory models are available. perceptual linear prediction, this is called PLP, only known as PLP. So, this details I will cover during the linear prediction analysis. This is called perceptual/linear prediction. Okay. Then SNP auditory model, Lion cochlear model, gamma tone filter bank model or inner ear or inner hair cell model. So, all are called auditory modeling of human speech processing. So, I just discuss one or two model and then you can study it. So, one model is that SNP auditory model. If you see what is auditory model. So, how human being perceive the speech sound I have to implement in auditory model. If you see there is a, so stage 1, stage 2 and stage 3. So, what is stage 1? What we have done? We have a series of basal membrane filter. So, I can say I can develop a basal membrane filter by a filter bank, nonlinear filter bank. So, there is a pre-filtering. Pre-filtering means since it is a digitized signal, so what I can do, I can develop a pre-filtering after ADC, so that high frequency and low frequency signal are cut up, and then I pass the signal through a band pass, or you can say the chunk of band pass filter, which is called basal we can say critical band filter. So, critical band filter bank. So, I have a speech signal, I pass this speech signal, let us forget the pre-filtering, pass this speech signal through a various frequency band filter. So, each filter output, or you can say the critical band filter output, give me the response of a basal membrane filter bank, each sensor. Now, I have to know which sensor is firing. I have to define which. So, this is called the hair cell firing. So, this hair cell firing I have to find out which filter is firing based on the collected energy at the output of the each filter bank. So, what this, so second stage is called, you can say the modeling of hair cell. So, this is called hair cell modeling. So, half wave rectification for find out the energy, then short term adaptation, synchrony residence, now rapid AGC, automatic gain control, then I can get the envelope detector, mean rate spectrum and synchrony detector, synchrony spectrum. Okay. So, I get a spectrum how human being perceive frequency at the output of this stage. Okay. So, details are here, stage 1, stage 2, stage 3 you can read. So, this is nothing but a idea is that I have a input speech, I pass through that is a chunk of band pass filter which is actually critical band filter, and each filter output is nothing but a sensor response. So, I calculate the response and I have to adjust that firing throughout that, you can say the amplitude compression, that part has to be done. So, that part I have done, and I calculate, I estimate the firing of the hair cell to perceive the frequency, that is called SNP auditory model. Then Lyon's cochlear model, same things. So, acoustic signal, outer ear, middle ear, pre-emphasis. So, acoustic signal is, if we pass through a, you can see we have a this kind of frequency response of the middle ear and outer ear. So, this can be pre-emphasized, signal can be pre-emphasized using inverse response. After the pre-emphasis, I can pass the signal through a chunk of filter. So, that is 86 cochlear filter bank, here it is designed, 86 cochlear filter bank in male or Bach scale. Okay. Then it is passed to the half wave rectifier to detect the amplitude, then AGC, automatic gain compression, to find out the frequency response of this acoustic signal as per the auditory response of human being. Okay. Then there is another model. So, this is the Lyon's cochlear, this I will come later on spectrogram. Then ensemble interval histogram, EIH model. So, the model of cochlear hair cell transduction. So, I can say along the basilar membrane there is a lot of there is a cochlear hair cell sensors. Each sensor consists of 10 fibers. Okay. So, that EIH, ensemble interval histogram, is nothing but a model of cochlear hair cell transduction. This transduction, this motion, how it is transduced, this motion to the transduction is take place, that is model here. How it is model? 165 channel equal space on a log frequency scale between 150 to 700 hertz, 150 channel filters, 165 channel filter. So, each cochlear filter design match neural tuning curve of for cats, minimum phase filter, array of level crossing detector that model motion of neural activity transduction of the inner hair cell, and then we sum it and get the response. Okay. Details you can also study if it is required. Then cochlear filter design, how it is designed, then EHI response, overall EHI response, that is EHI measure the spatial extent of coherent neural activity across auditory nerve. Okay. Okay. So, this kind of auditory models are mainly we use that PLP that we will discuss during the linear perceptual coding LP. When we discuss the LPC, that time we discuss the PLP details. Now, why these auditory models are important in human speech perception? So, nonlinear frequency scale. So, suppose I have a speech signal, I extract the parameter in linear frequency scale. Then physically I am doing is okay, that I can extract the physical frequency, but how human being perceive, that is important also to incorporate. So, if I want to incorporate that, then all this frequency scale of the signal must be nonlinear, which is logarithmic scale, either in Mel scale or Bach scale. Okay. Then spectral amplitude, dynamic range, timbre is an important parameter. Okay. So, spectral amplitude, dynamic range or compression or loudness log. So, if I see each tone has an amplitude. Now, perception of that tone, that particular frequency depends on the threshold of hearing. So, perception of amplitude for all frequency is not same. I have to go through the equal loudness curve. So, I can say spectral amplitude compression as per the equal loudness curve I have to do. So, I can dynamic range or amplitude of the spectrum has to be compressed as per the threshold of hearing. The hearing sensitivity of the human ear to the amplitude is not same or not equal to all frequency. So, as per the sensitivity is changing along the frequency. So, that sensitivity changing has to be modeled in spectral envelope also or equal loudness curve. Log spectrogram integration, temporal features. So, I can say the temporal features is very important in a speech signal. How the spectral dynamics is changing is also a part of a speech signal, also a features of a speech signal. So, that is also very important for speech perception. Timbre is one of that examples. So, suppose I am producing a signal, somebody else is producing a signal, same tone or same thing. Suppose that example I have already given, that suppose I am singing a song which is follow the same notation, same lyrics, same, you can say the duration is also same. I exactly copy my guru, but if you see the guru's sound, my sound cannot be equal because of complexity of the speech. So, dynamic of the spectrum is very much important to know the complexity of the speech. Okay. Then what to learn from the auditory model? If I say speech, once I say the speech, that if I say segmental and suprasegmental, or I can say the speech is not a stationary signal, it is not a pure tone, it is a stationary signal. So, it changes along the time. If I take a short duration 20 millisecond for a, let us say for a phone, and long duration for a speech segment, So, along the time property of the speech signal is changed. So, dynamics of the speech signal is changed. So, I can say 20 millisecond is also the parameter from the 20 millisecond is also in some kind of parameter we can get, and from long interval also we can get some kind of parameter which is also important for speech processing. So, temporal structure is very important for. So, I can say that speech contains both kind of information, not only the segmental information, suprasegmental information, across the segment information is very much important. You can do an experiment. Suppose you get a speech signal, you record a speech signal and find out the fundamental frequency for this segment. Okay, let us the fundamental frequency 200 hertz. Design a filter, or you can say that I can, okay, let us 0 to 200 hertz, design a 0 to 200 hertz filter, low pass filter, cut the signal. Again if you play the signal, you still perceive that 200 hertz is the fundamental frequency. How you got it? That means spectral dynamics told you the 200 hertz is the fundamental frequency. So, along the spectrum is also important, and you can see the segmental and suprasegmental both information are necessary. Okay? So, dynamic features is also necessary, how the spectral dynamics is changed, that also is necessary. Okay? So, dynamic features is changed in the importance, compression of loudness, compression of the scaling of the frequency, all are important, which is learned from the speech perception. So, in summary I can say how you perceive the intensity. Intensity is a physical parameter. So, how intensity related to the speech loudness is important. How the frequency, which is a physical parameter, is related to the perception of the pitch of the signal. So, human perception of frequency, human perception of loudness, and their mathematical model will be used in speech processing, so that my parameter extraction when I do, it should follow the human auditory systems. Okay? So, that is called speech perception. Okay? Thank you.